Hi everyone, welcome to the Software Development Essentials Workshop and the first of 5 total classes. This class is called The Fundamentals of Coding. This class is geared towards the following audience: entrepreneurs who are looking to build a software-backed product, professionals who either already find themselves in the technology space or are looking to break into it, students who are looking to learn some material they might not get in the classroom, and curious individuals who just want to understand more about how the modern world is being built. The objective for today's specific class is to understand the foundational concepts of code, algorithms, programming languages, and the background processes through which programs are compiled and executed. Fair warning, this class will be a bit more technical than the others since it will be setting up the foundation on which we'll build on in the classes going forward. So, this is our agenda for the evening. We're going to start with some quick intros and housekeeping so you know where I'm coming from, and then jump into the content. We'll cover bits and bytes, the definition of code, algorithms and programs, programming languages, how code gets executed and understood by the computer, some important aspects of code, and then finally, after the lecture, there will be a quiz waiting for you on the Teachable platform, if that's where you're watching this. But first, quick intro. My name is Kunal, and I'm from Edison, New Jersey. I studied electrical and computer engineering at Carnegie Mellon in Pittsburgh. I graduated in 2013. I worked as a software engineer for close to 5 years, decided to get an MBA, graduated in 2020, and now I'm a technical product manager at a fintech startup called Ridgeline. I had the privilege of learning computer science at an early age, and also had the privilege of continuing to develop those skills and have now worked in the technology ecosystem for close to 15 years. Why am I doing this? Mainly, it's because I think our world is in a very tough spot. Without getting into too much of a diatribe, but somewhat of a diatribe, today, those with the most means dictate and create the society we live in, either because of the privilege they were born with or because they managed to elevate themselves out of the realm of everyday common people and into their own echelon of society. They credit their success to their own hard work and ingenuity and choose to ignore the privilege, luck, happenstance, and head start, whether by nature of their race, their gender, or their financial nest, that they got in life. They instead convince themselves they earned it all by the nature of their sheer awesomeness. I don't owe society anything, right? I earned everything I have, and so other people can do the same. These folks with the most means at the top of the societal pyramid also by definition have the most lack of awareness of actual societal needs, because for the most part they're not affected by the problems faced by those below them on the pyramid. As the wealth distribution continues to get worse and worse, the connection to what's happening on the ground and what's actually needed grows thinner and thinner. So then we innovate for the sake of pushing boundaries in areas that don't actually need pushing, and then ignore the areas that actually need our attention. Because for those calling the shots, they have the means to remain unaffected by issues and crises that for many people is not a choice. This in turn creates more problems than get fixed, and the cycle gets worse and worse and goes on and on. Many will hear this and say, well, that's just market forces, man. If there's a market opportunity, it's just good business to push into that area. And to them I say, the market is what we make it to at least some extent. There's a feedback loop there, and the market consists of actual human beings, people. If we create a societal landscape in which the market values services X, Y, and Z, opioids, military caliber weapons, social media addictions, then maybe we should be asking why the landscape exists in the way that it does, instead of asking how we can make money off of its current state. Always remember, people can be convinced of many things that aren't actually true, and so they can also be tricked into thinking certain things are valuable by those at the top who have the most power and influence. And so, ironically enough, the people who have the perspectives and empathy and understanding for what actually needs to be done, because they've actually personally been affected by the things that are broken, are almost nowhere near the seats of power from which they can spark and enact change. Rather, their full-time jobs are surviving, paying the bills, paying off loans, having enough money to spend time with their friends and family, and praying that they one day make it to the promised land, the middle class. And there's definitely exceptions of wealthy people using their status to do some good, the Nipsey Hussles of the world, but they're pretty far and in between. And so, given that the people who I think are best suited to help fix our problems are often not enabled with the tools they need to do so, whether in business, government, or broader society, this workshop is in the spirit of trying to make a dent in that broken state. Everything we do today involves software, whether you're building AI to help predict and prevent international refugee crises, revamp the healthcare industry, build operating systems for vertical stack urban farming, build tools to help unfairly incarcerated citizens get access to the legal aid that they need, or build an industry agnostic salary tracker to help organize the quantitative case for equal pay. It's all built with code. My hope for this entire workshop is that this curriculum encourages and equips you as the viewer to be more informed in subject matter that is relevant to most operations that take place on this planet. For students especially, as the younger generation is looking around being like, yo, what the is going on? As a millennial, I can tell you I don't have the answers, but it doesn't take a rocket scientist to see that things are not looking good on many fronts. You as the future generations know more than anyone that we need change, and we needed it 20 years ago. I hope this material adds to your toolkit that you continue to build over your lives, and I hope that you get to take that toolkit and do something great with it. Some additional notes just to set expectations. I've never taught a workshop like this before, and I'm not a teacher. I have some experience teaching computer science at a K-12 school from a few years ago, some experience as an SAT tutor, and a non-trivial amount of experience helping my friends do their homework, but that's about it. I'm not a graphic designer, and so my slide designs are very basic. Try not to judge me for it. Content over presentation, always. I also have a stutter, which you might notice from time to time. All that said, I ask for your patience as I try out a new thing. Finally, some fun facts. I'm an INFJ on the Myers-Briggs assessment. My aspirational animal is a sea turtle, and I recently adopted a dog named Simba, who's perfection in every way. All right, and with that, let's jump in. That's a picture of Simba. Yeah, she's amazing. Okay, so I gave you this warning already, but I need you all to put your science and math hats on for this first class. I know it might be rough, but we need to cover this initial material so we can lay a foundation for everything that follows. I promise you after the first class, you won't need to do math for the rest of the sessions, but I do really believe that this material is necessary to see the full picture. We're going to cover important topics at a surface level, just so you can see how things are connected to each other. So let's start with the very basics and zoom in all the way to the physical components of code. I'm personally a visual learner, and it's important to me to understand how things are tied to tangible physical objects, and in the world of software, this can often be tricky. But let's give it a shot, and keep trying to give it a shot throughout these classes. So we're going to start by identifying the atom of computer software, the transistor, pictured on the bottom right. Our brains contain around 86 billion cells called neurons, one of which is pictured on the top right. They're the tiny interconnected little guys that form a massive network in your brain that let you think and remember things and make decisions. They help us remember instructions and commands that we tell ourselves to perform, otherwise known as programs, and they store all the memories we cherish and the facts and opinions that we like to bring up in our conversations to impress our friends. Similarly, computers contain billions of miniature entities of their own. They're called transistors, and they're made from silicon, a chemical element commonly found in sand. Transistors were first invented over a century ago and have revolutionized electronics ever since. In short, they are electrical components that you wire together in vast quantities, in the same way neurons in our brain are connected together in vast quantities. Billions and billions of them are configured and programmed to automate and control much of the world. But what are they, and how do they work? The simplest explanation is that transistors work as switches. A tiny electric current flowing through one part of a transistor can make a much bigger current flow through another part of it. In other words, a small current switches on a larger one. Looking at it another way, a transistor acts as an amplifier, taking a small input and outputting a larger one. All computer chips depend on a massive amount of transistors. We're talking billions to trillions on each chip, each of which can be switched on or off by toggling an electric current on and off through each transistor. You can just imagine how many different unique combinations you can get out of these billions of transistors, and in turn, what each of those unique combinations can mean. The neurons in our brain are similar. Neurons are electrically excitable, which means that if the voltage changes by a large enough amount over a short enough interval, the neuron generates an all-or-nothing electrochemical pulse called an action potential. So again, small change in input produces significant change in output. All or nothing, 0 or 1. Billions of those, which in turn encode everything we do and everything we remember. I make these comparisons because I hope you can start to see why computers are often compared to human brains, and why things like AI are so interesting/horrifying. The closer we get to being able to configure and operate transistors in the same way that neurons are configured and operated in our brains, the closer we get to robots which operate in ways that are indistinguishable from actual human beings. We are ourselves, biologically speaking, complex electrical circuits. That said, to assuage your fears of robot takeover, the difference/the good news is that there are things like love and soul and heart and faith and hope, which I believe can't be replicated, because they are in their essence irrational and illogical, and therefore cannot be configurable through a circuit in the way that we're discussing. So we'll always have those in our back pocket, even if the robots do come for us all. Anyway, the takeaway here is that when the electric input is on and flowing through the transistor outputs a large current. When the small current is off, the transistor outputs no current. And in this definition, a current is a flow of electricity. It's what flows through every electrical device. It's what makes light bulbs light up, what powers your computers and blenders and air conditioners. When you turn something on, the current starts flowing, powering the device. When you turn it off, the current stops flowing, turning off the device. Think of the flow of electricity in the same way you think of the flow of water. Let's say you had a pipe with water flowing through it that was attached to one of those old-timey water wheels. If the water failed to reach that wheel, the wheel would stop spinning. In the same way, if current fails to reach a light bulb, it will not light. So again, a transistor's only function is to amplify a current if it sees one. So it acts as a switch. When the transistor is on, that means it sees an input current and outputs a larger output current. It is a 1. When the transistor is off, it doesn't see an input current and therefore doesn't do anything. It is a 0. If you want to get into the nitty-gritty about how a small current can just produce a bigger current, because it's obviously not some sort of like sentient being that's looking out for a current and then pulling a lever to release a larger current, well, that gets more into the properties of silicon itself. But basically, it works by joining two silicon nodes together, with 2 electron-heavy nodes sandwiching an electron-lacking node. That's shown in the top image, with 2 electron-heavy nodes in red sandwiching an electron-lacking node in blue. One of the red nodes becomes the emitter, and the other becomes the collector. So normally, the base, the middle node, acts like a barrier between the two red nodes, preventing any significant current flow from the emitter to the collector, even though it really wants to, while the transistor is in its off state. But now let's connect the transistor up to some power. So suppose we attach a small positive voltage to the middle node, make the emitter negatively charged, and make the collector positively charged. Electrons are then pulled from the emitter into the base, and then from the base into the collector, and the transistor switches to its on state, outputting a large current. So it takes these electrons, which are currently sitting stagnant, and the input makes them flow, producing a larger output. Now, there's different kinds of transistors. The one on the top, a junction transistor, is a bit more straightforward to explain, so that's the one I went over here. But actually, the more commonly used one in the industry is called a MOSFET, which is a metal oxide semiconductor field effect transistor, which is shown in the image on the bottom left. While a bit more complicated, the important thing I want you to understand is that for either, the main concept is a small change in input that we turn on enables current to flow between opposing red nodes of the transistor, producing a larger output. So again, it takes a bunch of electrons that are sitting idle in the silicon material and makes them move, resulting in an output current. This is how a transistor acts like a switch. When it's in its off state, little or no current flows between the collector and the emitter. However, turn it on and the current does flow. So the input that we apply switches the transistor between its on and off states. The graph on the bottom right shows just that. At time equals 0, we turn on a small current, which in turn causes a large current, here with the value of 1, to be the output of the transistor. So again, the state of the transistor is either a 0 or it's a 1. Just to hammer this home, the transistor is our switch, changes from 0 to 1. To make this very simple, just visualize transistors as actual switches connected to a light bulb. The transistor can either be off or it can be on, 0 or 1. It only has 2 distinct states. All right, so let's shift gears away from circuitry and move on to some math. Again, I know a rough way to start the class, but I promise you that if you stay, we'll get through the math in this section and then never speak of it again. So, the decimal system is the system that we know. All of our ages, cryptocurrency balances, likes on Instagram, PSA, get rid of Instagram, population counts, everything is measured through the decimal system in our society. It's the system that we know and therefore often viewed as the only possible system that's out there. So first off, let's challenge that assumption. Let's look at the number 732, which is the area code of my phone number. Shout out to Central New Jersey. We see it, and most of us immediately visualize it and associate it to some pretty large quantity of objects. It's a handful of crates worth of oranges, or the number of attendees at an outdoor concert in the park, the amount of pranks that Jim played on Dwight, or the weight of an Icelandic pony, which, by the way, are ridiculously cute. We can grasp the number and make sense of its magnitude. But let's look more closely at 732 from a mathematical sense. How would we break it out to some extent? Well, we'd break it out into its digits. 732 is 7 hundreds, 3 tens, and 2 ones. What is 100? 100 is actually 10 to the second power. What is a 10? Well, it's 10 to the first power. And what is a 1? Well, it's 10 to the 0th power, because anything to the 0th power is 1. So 732 is 7 times 10 to the second power plus 3 times 10 to the first power plus 2 times 10 to the 0th power. So if you see the system there, we take the number that's at a given slot, multiply it by 10 to the nth power, where n is the position of that slot, counting up from 0 right to left. This is why it's called the decimal system. It's base 10. We count from 0 through 9, and then we add a digit. We then count 90 more times until 99, then we add another digit. Each slot has possible values 0 through 9. But this is only one way to encode information. So let's switch gears and change our perspective to the binary system, which is base 2. Decimal, dec, the prefix is 10. Binary, bi, the prefix is bi, that's 2. The language that computers understand is binary. Beep boop, beep boop. So here's a new number. 1011 0111 00. In base 2, instead of counting from 0 to 9, we simply count from 0 to 1, and then we add a new slot. So we take the number that's at a given slot, multiply it by 2 to the nth power, where n is the position of that slot, counting up from 0, right to left. So given what we just did to convert our base 10 number to a more abstract form and determine its value, can we do the same here to figure out what the value of this binary number is in base 10? So let's break it out. We have slots. So if we look at it here, if we go left to right, we have 1 times 2 to the 9th, plus 0 times 2 to the 8th, plus 1 times 2 to the 7th, plus 1 times 2 to the 6th, plus 0 times 2 to the 5th, plus 1 times 2 to the 4th, plus 1 times 2 to the 3rd, plus 1 times 2 to the 2nd, plus 0 times 2 to the 1st, plus 0 times 2 to the 0th. And just so that everyone sees that, look at the leftmost slot in this number, the first one all the way to the left. That means that we multiply that number by 2 to the nth power, where n is the slot of that number, right? So you can see that the numbers that are not in red, if you order them, it's the order of the number that you see. And if we do that math and we get 512 plus 128 plus 64 plus 16 plus 8 plus 4, because all the zeros, just anything multiplied by 0 is 0, then we get 732. So it turns out it's the same number. So binary is just a different format of representing data. It's a different way to encode data, with each place only having 2 possible values, 0 or 1, on or off. So again, there's slots, which represent the power of the exponent, and the base, which represents the base of the exponent. So base 16, which is known as hexadecimal, would count from 0 through 15 in each slot. And for those of you who are wondering, it goes 0 through 9 and then A through F. So you start using letters. So 732 in hexadecimal is represented by 2 D as in Delta, C as in Charlie. How binary ties into actual software we'll get to in a second, and maybe you can already put it together thinking about switches on and off, 0 and 1. But for now, understanding what binary is the important part. So let's count to 15 in binary. For zeros, we know 0, 0, 0, 0 just represents the number 0. If we wanted to add 1 to that now, 0, 0, 0, 1, we get the number 1. If you added 1 to that, well, now we know that the maximum possible value for any slot is a 1. It's not a 9 because this is binary, so it's either just a 0 or a 1. So now when we add 1 to 1, it actually carries to the next slot. So 2 is 0, 0, 1, 0. This would be the same case if we were at the number 9 and we added 1 and it became 10, right? Except this is from 1 to 2 because a given slot can only occupy the value 0 or 1. So number 2 is 0, 0, 1, 0. If you add 1 to that, well, we have a 0 available in the first slot, so that can bump up to a 1. So 3 is 0, 0, 1, 1. If we add 1 to that, well, now the first and second slots are both 1s, so we carry all the way to the third slot. So number 4 is 0, 1, 0, 0. Add 1 to that, we get 0, 1, 0, 1, that's 5, 0, 1, 1, 0, that's 6, 0, 1, 1, 1, that's 7. Now if we add 1 to that, well, now all 3 of our slots, our first 3 slots, are occupied, so it carries all the way to the fourth slot. So 8 becomes 1, 0, 0, 0. If you add 1 to that, well, now we have a free slot in the first slot, so you get 1, 0, 0, 1, that's 9, 1, 0, 1, 0, that's 10, 1, 0, 1, 1, that's 11, 1, 1, 0, 0, that's 12, 1, 1, 0, 1, that's 13, 1, 1, 1, 0, that's 14, and 1, 1, 1, 1, that's 15. And so you can see with 1, 1, 1, 1 that if you wanted to translate that into like what number that represents, you would take the value at each slot and multiply it by 2 to the nth power, where n is the position of that slot. So since we have 4 1s in the number 15, 1, 1, 1, 1, you would do 1 times 2 to the third, plus 1 times 2 to the second, plus 1 times 2 to the first, plus 1 times 2 to the 0th. That would get you 8 plus 4 plus 2 plus 1, which is 15. So something that we'll get to in a second, but you can see here that with n slots, you can have 2 to the n unique combinations in binary. In decimal, that number would be 10 to the n, right? So if you had two total digits, that's 10 to the n unique combinations. That's 0 through 99. That's 10 to the second power. In binary, 2 slots can only get you 4 possible numbers. That's 2 to the second. So you can, again, if you just look at the first 4 numbers here, you can have 0, 1, 2, or 3 represented by 2 slots. If you increase that to 4 slots, then you get 15 possible combinations. So moving on to some definitions and introducing the terms bits and bytes. So similar to how a digit can hold a single decimal value, 0 through 9, a bit can hold a single binary value, 0 or 1. A bit is atomic. It's the smallest unit of storage, and anything with 2 distinct states can be stored into a single bit. 0 and 1, on and off, true and false, yes and no. And so, as we just mentioned, how many distinct patterns can you make with 1 bit? 2. 2 to the first. With 2 bits, 4, 2 to the second. With 3 bits, 8, 2 to the third. So mathematically, n bits yields 2 to the n patterns, 2 to the nth power. A byte is a collection of 8 bits, which results in 256 unique combinations. You can count from 0 to 255, or you can have 255 unique representations of some other thing. An example is 10101101 is 1 byte, and it is the number 173 in decimal format. Some notes about bytes. All storage is measured in bytes, despite requiring very different hardware requirements for different amounts of bytes. Kilobyte, KB, is about 1,000 bytes, which is 1,000 collections of 8 bits. Megabyte, MB, is about 1 million bytes. That's 1 million collections of 8 bits. Gigabyte, GB, is about 1 billion bytes. And a terabyte, TB, is about 1 trillion bytes. So all the storage that you see on all your hard drives and RAM and whatever else, those are all measured in these terms. And so now you know, like, a byte is just a packet of 8 bits. So the next extremely important visualization to really nail into your brain is that bits correlate to transistors. While it's not true that 1 bit corresponds to 1 transistor, since that would be too simple, and we're not going to get into why that's not the case because it's more complicated than I want to get here. A few, in this diagram on the left, 6 transistors together can represent a single bit and its read-write capabilities. And again, a bit can either be a 0 or it can be a 1, and a transistor can either be on or off. So whenever you see things like 8 gigs of RAM or 1 terabyte hard drive, it's literally referring to how many individual zeros and ones, and thus how many individual transistors scaled linearly can fit into the memory of a computer or onto that physical hard drive device. So with 1 terabyte, that's 1 trillion bytes, which is 8 trillion bits, which is something like 48 trillion transistors. And those transistors, again, are physical electrical components. So to fit 48 trillion of them into a space, you have to imagine how small we can make them now. On that note, we're not going to cover it in this class, but I'm sure you've noticed how over time, hard drives have gotten smaller and smaller, as have our laptops and desktop machines. A 1 terabyte hard drive used to be a brick. Now it's the size of your wallet. This is because the name of the game is 1, how small can you get your individual transistors? And 2, how many transistors can you fit into an object of a given size? There have been many innovations on both fronts over the past decade, including others like the development of SSD hard drives to replace HDD hard drives. Companies like Western Digital and Qualcomm invest a lot into this space. Super interesting stuff from a hardware standpoint, but not the focus of this class. Maybe hardware will be by next iteration. Let's see how this one goes first, though. So now we know that bits and bytes store data through the use of transistors. But how is that actually possible with the types of data that we see in our everyday lives? How can things like letters, documents, images, videos, whatever else we see and use on computers be stored as zeros and ones? Well, it's a great question. So let's start with ASCII. ASCII is an encoding representing each typed character by a corresponding binary number. Encoding is the process of converting data from one form to the other. So ASCII encodes 128 specific characters into 7-bit binary numbers. For example, the capital letter A is encoded as 01000001, and the ampersand symbol is encoded as 00100110. This table shows the complete set of encodings in ASCII. The encoded characters include the digits 0 through 9, lowercase letters A to Z, uppercase letters A to Z, and various punctuation symbols. In addition, the original ASCII specification included 33 non-printing control codes, like the carriage return and the tab codes. ASCII was the most common character encoding until the World Wide Web. You started using UTF-8 in December 2007. UTF-8 is basically the same thing as ASCII, but expanded on the value set. So instead of using 7 bits, it now used 8-bit numbers, which doubled the amount of characters it could encode. So things like the /, the \, the percentage sign, and the pi symbol were added as elements to UTF-8. UTF-8 is backwards compatible with ASCII, which means that the capital letter A is encoded in the same way in both systems. UTF-8 is by far the most common encoding for the World Wide Web, accounting for 97% of all web pages as of 2021. Unicode is another encoding system used for characters in Mandarin or Greek or Arabic or emojis. Typically, Unicode needs to use 2 bytes to encode each character. Images are encoded using pixel positions on a grid and color codes. So let's say for a black and white picture, to keep it simple, you can imagine each pixel of the image either being on, black, or off, white. Then an 8 by 8 pixel image can be rendered by just 64 bits of information, representing the grid of black and white dots that the image is comprised of. Obviously, things like colored images and videos and more complicated objects need a more sophisticated system. But the important takeaway here is at the end of the day, anything can be converted to binary, assuming there is a scheme or a standard in place to dictate the rules of conversion. In turn, anything can be represented by bits, zeros and ones, which in turn are represented by transistors, the physical devices, the physical components on all your devices. So 1 byte works well for encoding individual characters, as we've seen, but computers are also good at manipulating numbers. So let's say you wanted to just build a simple calculator application that takes numbers and performs basic arithmetic operations on them. So again, we're differentiating here between the character representation of a number and a number itself. The character 2, which is what you would type into a document or send in a text message, is different from the number 2, which is what you would use in a calculator. For numbers themselves, you can just use binary as a simple counter, with the leftmost bit serving as the plus minus sign of the number. So again, go back to our example where we counted from 0 through 15. Integers are typically stored with either 4 or 8 bytes. 4 bits can count from -8 to +7. And we'll get into how the positive and negative thing works in just a second. 8 bytes can count from -2147483648 and 2147483647. Adding in binary is just like normal addition with carrying, as we saw before when counting from 0 to 15. But when you run out of bits, you can't carry anymore because that leftmost bit indicates sign. So carrying to the leftmost bit actually changes number from positive to negative, which can lead to problems, which we'll see in just a second. So we can see here just how 4 bits can hold the numbers -8 to +7, assuming the leftmost bit flips the sign. So you can see the two columns here have both the unsigned value and the signed value. The unsigned value is if the leftmost bit does not represent sign. That's what we did in the previous example, right? We started at 0 and we counted all the way up to 15. The signed value on the other side, on the right, we can count from 0 to +7. So you can go from 0 to 0, 1, 1, 1. Then when you add 1 though, then the leftmost bit also flips the sign of the number. So 1, 0, 0, 0 is actually -8. And then when you add 1 to that, it becomes -7. You add 1 to that, it becomes -6, all the way to 4 ones, which represents -1. So it's a bit confusing, but it's how we equalize the range on either side of the 0 with a given number of bits. So 4 bits can either be used to count from 0 to 15, or if you shift that over to include some negative numbers, -8 to +7. So those are the two different ways that you can use a given number of binary slots to represent numbers. So let's say for every game that's in the App Store, it has a maturity rating. The maturity rating ranges from 0, anyone can play this game, to 7, only adults should play this game. Let's say then that tomorrow we want to add a rating at the base of the pyramid, specifically indicating that this game is only really meant for kids. So every game that was a 0, general audience game, becomes a 1, and every 1 becomes a 2. So now all, and like so on. So now all 7s, which are the games with blood and gore and mature language, are bumped from a 7 to an 8. But we only have 4 bits for our rating, which means the leftmost slot, the 4th bit, changes the sign of the number. So adding 1 to 7 doesn't make it an 8, it makes it a -8. So now every mature game is actually rated -8. And if the logic that's in the App Store says, for users whose accounts show that they're under the age of 18, show me all of the apps whose rating is less than 7, so that they would not show them mature rated games, well, -8 now falls into that range. So now kids are seeing Halo and Grand Theft Auto and whatever else. A similar scenario actually happened when I was working on an App Store team, and is an example of what is referred to as integer overflow. When you've maxed out on the positive numbers that can be represented by a certain amount of bits, adding 1 to that max, in this case 7, results in the negative extreme, -8. Alternatively, if you only have 3 available bits and your numbers are unsigned, which means there's no bit that indicates the sign, and you hit a max of 7, and then you add a 1 to it, you would just get a 0, right? You would carry that 1 all the way through to a 4th slot that doesn't exist, and the rest of your numbers would turn to 0. And so regardless of if it's signed or not, that's an example of what's called integer overflow. So anyway, just a quick aside as to some of the things you have to account for when building software. Adding 1 to a number can result in either a negative extreme or it can result in a 0, and that's not what you might expect when you normally think of doing math. So up to this point, we've covered what we need to know to understand how computers process and store data. So now we understand how any piece of data can theoretically, at least, be converted into zeros and ones and stored into bits and bytes. You just need a system. You need a schema in place, whether that's ASCII or not. Making the comparison back to our brain, we should now understand memories and facts and things that we know. That information is encoded, stored somewhere. But now what about logic? How does a computer actually make choices and make decisions? Converting everything in our world, text, images, videos, whatever, to binary data and storing it is one thing, but programming a computer to actually do something at certain junctures is totally different. That gets us into more logical decision making as opposed to storage of information. So now we're going to take a deep dive into a very universal question. What is logic? According to Wikipedia, logic is the systematic study of valid rules of inference, the relations that lead to the acceptance of one proposition on the basis of a set of other propositions. More broadly, logic is the analysis and appraisal of arguments. There is no universal agreement as to the exact definition and boundaries of logic. However, it has traditionally included the classification of arguments, systematic exposition of the logical forms, the validity and soundness of deductive reasoning, the strength of inductive reasoning, the study of formal proofs and inference, including paradoxes and fallacies, and the study of syntax and semantics. Now, this is some philosophical meta type stuff that we don't need to get too deep into, but I want everyone to understand real quick how important that fact actually is and how rooted in math and philosophy the entire discipline of software and computer science is. Put another simpler way though, logic is a set of true and false conditions built using the information we have at hand, through which conclusions can be drawn, generating new information. Applying this back to transistors and bits, what does this mean? Well, we can put a few transistor switches together to make something called a logic gate, which compares several input currents and gives a different output current as a result. A finite set of transistors for each input condition and another for the output conclusion. And again, just to show you how it relates back to the brain, that's exactly how neurons work as well. Logic gates let computers make very simple decisions using a mathematical technique called Boolean algebra. It's the branch of algebra in which the values of all the variables, input and output, are the truth values, true and false, usually denoted by 1 and 0, respectively. So now instead of using bits to just encode and store values, we can now use stored values to evaluate true and false conditions, which can also then be encoded as 1s and 0s, and generate output values in the form of conclusions through those inputs, which again can also be encoded as 0 and 1. Conclusions through true and false conditions. Let's dive a bit deeper into this though. Your brain makes decisions in the same way we just mentioned. Using inputs, things you know, you can produce outputs, make decisions. Let's look at a few examples. I can say, if it's raining and I have an umbrella, I will go to the park. If it's raining is an input condition. It can either be true or it can be false. If I have an umbrella is another input condition. It can either be true or it can be false. Then I will go to the park. That's a conclusion. It can either be true or it can be false. That's an example of Boolean algebra using what's called an AND operator. The word operator is just a bit of mathematical jargon to make things seem more complicated than they are. You can make similar decisions with other operators. If it's windy or it's snowing, then I will not be going out, is an example of using an OR operator. So, using AND, OR, and other operators called NOR, XOR, NOT, and NAND, computers can compare a given amount of binary number inputs and produce another binary number as output, based on the operators being used. That idea is the foundation stone of computer programs, the logical series of instructions that allow computers to do certain things based on certain pre-existing conditions. So let's take a look at some of the most commonly used logic gates that are out there and are ultimately used to build every piece of software in existence. Again, each of them has n inputs, where n can be a number 2 or larger, and a single output. So a NOT gate. You have a single variable a, and the NOT is the hat that's above it. So if a has an input of 0, then the output is a 1, right? So if it is rainy, I am not going out. So if it has an input of 1, it becomes a 0. If it is rainy, that is true, that is a 1, then I am not going out. The output is a 0. If it is not raining, input is a 0, I am going out. Output is a 1. So the NOT gate flips your input, right? The input condition, if it is true, the output is false. If the input condition is false, the output is true. And you can define that input condition qualitatively however you want. In this case, I've used is it raining and am I going out as the input and the output respectively, but it can be anything. So that's the NOT gate. The AND gate takes 2 or more inputs, which is different from the NOT gate. The NOT gate takes in a single input. The AND gate with 2 inputs says the output is only 1 true if both the inputs are also 1, right? So if the input is 0, and if the input B is 0 and the input A is 0, then the output is 0. If the input B is 0 but the output A is 1, the output is 0. If it's 1 and 0, it's still 0. Only when A and B are both 1 is the output 1. So the qualitative statement here could be, if it is sunny and it is warm, I'm going out. If it's sunny and it's cold, I'm not going out. If it's rainy and it's warm, I'm not going out. If it's rainy and it's cold, I'm definitely not going out. But there's actually no definitely there. All zeros are treated equal. So anyway, the NAND gate is you take the AND gate and you invert it, right? So now the only time I'm not doing something is when both my inputs are true, right? So if I change my inputs to mean rainy and cold instead of sunny and warm, if it is rainy, 1, and it is cold, 1, I am not going out, 0. So the only time when the NAND gate outputs a 0 is when both inputs are true. So you can see it's the AND gate, but flipped. All the 0 outputs turn to a 1, the single 1 output turns to a 0. Or, this one is a bit more like lax in terms of its rules. It says that if any of the inputs is a 1, the output is a 1. It's an OR gate. So the only time when the output is 0 is when both the inputs are 0. 0 and 1 produces a 1. 1 and a 0 produces a 1. 1 and a 1 produces a 1. 0 and 0 produces a 0. So if it is sunny or if it is warm, I'm going out. If it's sunny and warm, I'm still going out. If it's sunny but it's cold, I'm going out. If it's rainy but it is warm, I'm going out. The NOR gate is the opposite of the OR gate. It's the inverse of the OR gate. So here, the only time the output is a 1 is if both the inputs are zeros. So if it is rainy or if it is cold, I am not going out. The only time I'm going out is if it is not rainy and not cold. It's the inverse of the OR gate. XOR. This one is kind of like the in-between between the OR and the AND, where it is an exclusive OR. The output is only 1 when one of the inputs is a 1. So 0, 0 produces a 0, 0, 1 produces a 1, 1, 0 produces a 1, 1 and 1 though produces a 0. So this is like saying only if it is either sunny or warm, I'm going out. If it's both, I'm not going out. If it's neither, I'm not going out. But if it's sunny and it's cold, I'm going out. If it is rainy and it's warm, I'm going out. So the XNOR is the inverse of that. Only if it is both sunny and warm, or it is both not sunny and not warm, I'm going out. So it's only a 1. The output is only a 1 when the inputs are either both zeros or they're both 1s. If there's some mix of zeros and 1s, the output is a 0. So those are the main logic gates, and I know like the rainy, sunny example kind of gets a bit muddied, but that's you can, again, the qualitative ways that you view your inputs and your outputs can be anything, right? It can be, if I tear my ACL, I'm not playing soccer. If I get a good grade on this, I am getting ice cream on Friday, or like whatever it is. But the zeros and ones are what represent those conditions as the inputs, and the conclusions as the outputs. And they can all be boiled down to zeros and ones. How you define what those mean, that's up to you. So this is just a helpful visualization, I think, at least. Here, there's two different images. It's from a 2015 article by Paul Ford called "What is Code?" If you wanted to Google it. But on the left here, you can see inputs. So you can see on the leftmost image there, the top two have inputs of 0 because they're both off, and the bottom 6 are on. And you can see how those inputs flow into like layers of logic gates. And then all the way at the very end, on the right side of the image, you can see which outputs are 1 and which outputs are 0. So again, you can create really complex networks of logic gates. And then based on how you toggle your inputs and which logic gates you have defined in your sequence, you can create a very unique set of outputs. And this middle part of each drawing is what represents like the logic of a given computer program. So it'll have a certain set of inputs. It'll take and do a bunch of things on those inputs. So it'll say, based on these inputs, do this thing, then take the output of that, and based on this other input, do this other thing. And it can go through a number of layers of that, but ultimately it'll produce an output. And so you can just kind of see like, take this image, and this is simplified, right? So you can, in terms of how computer programs, the complexity that they can get and how that ultimately boils down to logic gates, like you can't put that in a drawing. This is just an attempt at trying to understand like how that could look like. So anyway, this is how logic gates can be stacked together. And you can also see the important thing here is like outputs of gates can be inputs into the next level of gates. So an output from one gate can be the input to another gate. You can have raw inputs, which maybe come from the user. But there's levels to it. So now that we have a decent understanding of how both logic and various types of data can be represented through bits, let's now zoom out one step further and talk about algorithms. Algorithms are both a funny word, algorithm, where the prefix means pain and rhythm means a strong, regular, repeated pattern of movement or sound. So it's a pattern of fixing pain, or interpreted differently, a pattern of pain itself, which I think is kind of funny and weirdly accurate. But what is an algorithm? In computing, algorithms provide computers with a guide to completing actions. They're comprised of a precise series of steps that outline exactly how to complete a task and solve a problem. You could consider a cake recipe an algorithm for making a cake, or the dental steps involved in giving a patient a filling, or the steps involved in doing and folding your laundry. All an algorithm is, simply, is a set of instructions to complete a task. A great algorithm gets a name. Many algorithms have their own pages on Wikipedia. You can spend days poking around them if you choose to, but I'd recommend against that. Euclid's algorithm, as an example, is a set of instructions used to determine the greatest common divisor for two numbers. So what does that mean? Take two numbers, like 16 and 12. What's the largest number that can divide each of those two numbers without producing a remainder? How do you find that? Well, the steps are, you first divide the larger number by the smaller number. So I divide 16 by 12. If there's a remainder, in this case there is, then it's 4, you divide the smaller number, 12, by that remainder, which gives you 3 and a remainder of 0. If there is a remainder, you continue to divide the smaller of the two numbers from the previous step by the remainder of the current step until you get to an outcome with no remainder. The last number you divided by to end up with a result with no remainder, that number is the greatest common divisor. So again, this is an example of an algorithm, a series of steps to complete a task, which in this case is finding the greatest common divisor of two numbers. So in 16 and 12, we divide 16 by 12, we get 1 with the remainder of 4. Then we take the smaller number, 12, we divide that by the remainder, 4. That's 3 with the remainder of 0, because that divides cleanly. So then that 4 is the greatest common denominator. If we change 16 to 17, 17 divided by 12, you get 1, remainder is 5. You then do 12 divided by 5, you get 6. No, you get 2, remainder is 2. And then you get the smaller number 5 divided by that remainder, which is 2 with a remainder of 1. And then you take the smaller number, 2, divide that by 1, and then you get a remainder of 0, because 2 divided by 1 is 2, with no remainder. Now, here, 1 is the greatest common denominator, right? You can look at the numbers 17 and 12. 17 is prime. So it's only divisible by 1 and itself. And so it makes sense that 1 is the largest number which divides both 17 and 12. Whereas 4 times 3 is 12, 4 times 4 is 16. That also makes sense when the number is 16 instead of 17. Cool. So that's an algorithm. Moving on to programming languages. The act of programming is writing sets of instructions, algorithms, for a computer to execute. If you've ever cooked using a recipe before, you can think of yourself as the computer, or your brain as the computer, and the recipe's author as a programmer. The recipe author provides you with a set of instructions, which you read and then follow. The more complex the instructions, the more difficult it is for you to execute. In the same way, a programmer would write a program to give to a computer, which would then read the program and execute the instructions it reads. Programming languages, then, are the tools we use to write instructions for computers to follow. A programming language is made up of a series of symbols and syntax that serves as a bridge that allow humans to translate our thoughts into instructions computers can understand. Ultimately, remember that computers think in binary. So there's a translation that has to happen when a programmer writes code and when a computer receives it in binary and executes. But we'll get to that in a little bit. I think one helpful thing to remember is that lots of times we gloss over the fact that a programming language is, at the end of the day, a language. It has syntax, it has rules, it has ways to read it and write it, it has meanings, nuances, structure. The only real difference between English and Java is that English is processed and understood by our brains, and Java is processed and understood by our computers. I'm sure all literature majors who are watching this are sick to their stomach, and I'm sorry. And the other thing to mention is, I guess at this point, English can also be processed by a program that's written in Java, which is kind of cool and kind of scary to think about. That's how things like Siri work, through natural language processing known as NLP. But going back to the cake example, let's say it's tres leches. English is the programming language that's used to write the program, assuming an English cookbook. That's the recipe. That is then understood and executed by our brains, the computers, to bake a cake. But what are the differences between programming languages? Why are there so many of them? Why can't we just use one and call it a day? Well, unfortunately, it's not that simple. It never is. So, let's start with two important buckets and then we'll split those out even further. First, let's differentiate between low-level and high-level programming languages. Low-level programming languages are closer to machine code or binary. Therefore, they're more difficult for humans to read, although they're still easier to understand than ones and zeros. The benefit of low-level languages is that because they're closer to ones and zeros, they're fast and offer precise control over how the computer will function. You can imagine languages like this actually interacting with bits and bytes of data. Change the bit at position X from 0 to 1. Move this byte of data from this place to this other place, where the places are represented by addresses in binary. High-level programming languages are closer to how humans communicate today. High-level languages use words like object and order and run and class and request, and etc. that are closer to the words that we use in our everyday lives. This means they're easier to program in than low-level programming languages for human beings, but the downside is that they do take more time to translate into machine code and binary that the computer will then understand and act on. The good news, though, is that as computers have become more powerful, the difference in the time this translation takes between low-level and high-level programming languages is often very small, only milliseconds. As a result, high-level languages do the trick in most scenarios when it comes to building software. Again, try and view this as an analogy to actual human languages. We started off however many millennia ago with some basic hand signals and hooting and hollering to relay thoughts and feelings about immediate needs, which then evolved over time to much more nuanced and complicated forms of communication, whether it was Sanskrit or Latin or emojis or dank memes. While languages like Sanskrit and Latin are obviously more complicated and nuanced than hand signals, as our minds have evolved and become more powerful over time, the difference in time taken for comprehension between understanding Latin and understanding hand signals, hooting and hollering, has been reduced dramatically. Same situation with the evolution of programming languages. Computers today are basically just as efficient at understanding zeros and ones as they are understanding Java and Python. They just need to be given an instruction manual, like how humans need to be taught the basics of a given language before they are fluent in it. Diving deeper into the differences between programming languages, it's important to note that even within each bucket of high level and low level, there are notable technical differences between different languages. The first one is syntax. This is as simple as understanding the difference between German and Swedish and Swahili. Words mean one thing in language A and are literal gibberish in language B. They may share some root words and overlap in certain ways, but for the most part, they are completely independent. There are different ways to structure sentences, phrases, punctuation. There is a different order to nouns, verbs, adverbs, articles, etc. Similarly, in programming languages, there are many different ways to define variables, order logic, and ultimately, different ways to give the computer instructions to do different things. The second important difference is how the language is interpreted and translated. We'll get more into this a bit later, but think about how you process images versus text. You see the color green on a traffic light and you know, okay, I can go now. Someone could also be in your passenger seat and tell you directly, okay, you can go now. One method is processed as a visual image, which you can extract meaning from. The other is processed as a string of words directly, which you can then extract meaning from. Similarly, different languages are ultimately processed and converted to zeros and ones in different ways. Third is memory management. This is basically the question of, are you responsible for the data storage associated with your programs, or is there a background process that's allocating space and garbage collecting unused data on your program's behalf? Some languages require you to manually take care of this yourself, like C. Others have it automated on your behalf, like Java. This one is a bit more complicated in nature, so we're not going to get into it too much. Don't worry about it too much. All of these technical considerations, though, along with more, in turn produce the fourth and arguably the most important difference, which is the utility of a given language in the real world. Given all the technical considerations that we just mentioned and more, and given what your specific use case is, which language makes the most sense for you? So let's dive into that utility point a bit more by looking at some of the most popular programming languages internationally today and what they're used for. So GitHub's PyPL index ranks programming languages according to how often tutorials are searched on Google. The most popular programming languages include the following: Python, Java, JavaScript, C#, C/C++, PHP, R, Objective-C, TypeScript, Swift, Kotlin, MATLAB, Go. So as you can see, there's a lot of them. And you can it's kind of cool seeing like the percentage share. So Python, is like 31% of the market, and since 2020, it has trended 1.1% downwards. So that's some interesting information. So diving into some of the ones listed there, just to go over them at a high level. Python. Python is a versatile general-purpose programming language. It can be used in a variety of fields, from data science and machine learning to web development, and it's a great first language to learn. Java is another language that's great when you're starting out. Java can be used for many things, including mobile apps, software development, and large systems development. AP Computer Science is currently taught in Java, so it's a very foundational language in a lot of ways. JavaScript is primarily used as a front-end language, and we'll get into what that means later. But that manages client-side behavior, so it enables web applications, game development, and mobile applications. C#. C# is Microsoft's popular programming language, and it can be used for a wide variety of applications, including game development, enterprise software, video games, mobile apps, and more. C, along with Python and Java, C forms a good foundation for learning how to program. It's one of the first programming languages ever developed, and C has served as a foundation for writing more modern languages and is an easy language to debug, test, and maintain. However, it is an older programming language, and it's not necessarily suitable for more modern use cases such as fancy websites and mobile applications. C++ is one of the most powerful programming languages out there as well, and is used in a wide range of industries, including VR, software and game development, robotics, and scientific computing. PHP is a widely used server-side language. It's a great choice if you're interested in building dynamic web applications and works well with databases and with HTML. We'll get into what those things are later. R is a statistical programming language that's popular among data scientists. It's used for answering questions with data analysis and for creating data visualizations. So a lot of professors, typically ones who are doing their own research or studies, they'll use R pretty commonly. Swift is Apple's programming language and is a must if you plan to develop applications for iOS and Mac. Kotlin is an open source programming language developed by JetBrains. It's popular for web development, Android development, and more. And Go is also referred to as Golang. Go is developed by Google to be an efficient, readable, and secure language for system-level programming. It works well for distributed systems in which systems are located on different networks and need to communicate by sending messages to each other. Don't worry about that too much, but Go is a pretty new language, but it has a really large library and extensive documentation, which makes it very usable. Outside of formal languages, though, that are developed over time and put out there by various organizations as they are created, pseudocode is another really important construct to consider. Pseudocode is a plain language description of the steps in an algorithm or another system. Pseudocode often uses structural conventions of a normal programming language, but is intended for human reading rather than machine reading. So computers won't understand pseudocode. It's often very important when you're brainstorming and developing solutions in a language agnostic manner. This is the language in which you, as founders potentially, can learn to talk in to help think through problems with your engineering team. All it really requires is a logical mindset and thinking through things in terms of concrete steps and logical forks. So let's expand on this by looking at an example. So let's go back to Euclid's algorithm. If we remember, the steps of the algorithm are: you divide the first number by the second number. If there's a remainder, you divide the smaller number by the remainder. If there's still a remainder, you continue to divide the smaller of the two numbers from the previous step by the remainder until you get to an outcome with no remainder. The last number you divided by to get a result with no remainder, that number is the greatest common denominator of your two original numbers. So there's a site called Rosetta Stone that shows you different algorithms in different programming languages. The Euclid's algorithm page is pretty great, and here you can see the algorithm in a few different programming languages. A lot of this should probably appear like gibberish to you. You have to learn all the various syntactic rules, structure, and nuances of each programming language, which can take weeks or months or years for any given language. There are some things I want you to note, though. You can see logic gates, right? If the remainder of a % loop is 0 and b % loop is 0, do something. You can also see data storage. Create a variable called factor and give it a certain value. All of these programs are composed of conditional statements used to make decisions and storing data into variables. That said, on the other hand, pseudocode is very much immediately available to you. So how would we write Euclid's algorithm in pseudocode? Well, it looks something like this. You're given two numbers, m and n, as inputs. If the value of m is less than the value of n, you switch the values of m and n. So you always want the larger number in m and the smaller number in n. Then you find a number r equal to m modulo n. And modulo is give me the remainder. So m modulo n will give you the remainder of m divided by n. So 16 modulo 12 will give you r as 4. So then you say let m have the same value as n, and let n have the same value as r. If n does not have the value of 0, go back to step 2. Then when you break from 6, when you break out of step 6, so when n does have a value of 0, then step 7 just says the greatest common denominator value is in m, which is the output. And again, I want to point out here that ultimately code can be broken out to data storage and logic. If this, then do that, and assign this value to this variable. Store this value in this variable. And so now the question that everyone asks all the time is, well, which programming language should I use for my use case or my software product? And the answer is, well, it depends. It's all about the utility that a language provides and how it fits with what you're trying to build. Some questions to think about are, which languages are lightweight versus heavyweight from a memory usage standpoint? Which ones are the most intuitive and easy to learn from a team perspective? Which ones are more suitable for front-end versus back-end development? And is your application more front-end heavy or back-end heavy? Which ones are only compatible with certain physical devices or operating systems? And do you care about that? One common example here is, are you building an iOS app or an Android app? Which ones are better for mobile development versus web development? Are you building a phone app or are you building a website for laptops? These are all questions that require an awareness of the landscape of programming languages, which is constantly changing. Languages are being deprecated, others are being added, others are being modified and expanded. All that said, many things can be done in many different ways, and oftentimes it just boils down to personal preferences. That developers have their own favorites and will oftentimes die on the hill of whatever programming language they've used the longest or know the best. Or alternatively, they'll refuse to join a company that uses a given language given their own experiences with it. So you really have to be careful and do your research for your specific use case. A good CTO or engineering lead will have the answer to this question of which programming language to use and should be able to back it up as well. All right, so at this point, we hopefully understand what code is, how it's organized into languages, and now how do these languages somehow get translated into zeros and ones that the computer understands. We're not going to get too much into the weeds here, but that process takes us through something called a compiler. A compiler is a special program that processes statements written in a particular language and turns them into machine language, or code that a computer's processor uses and understands. This is binary. Typically, a programmer writes language statements in a language, such as Java or C, one line at a time, using an editor or in an IDE, which stands for an integrated development environment. The file that is created contains what is called the source code. The programmer then runs the appropriate language compiler, think like the Rosetta Stone, specifying the name of the file that contains the source statements. When executing programs, the compiler first parses all of the language statements in your program, one after the other, and then in one or more successive stages or passes builds the resulting output machine code, binary, making sure that statements that refer to other statements are referred to correctly in the final output. So traditionally, the output of the compilation is called an object module. The object module is the machine code that the processor can understand and execute one instruction at a time in zeros and ones. And there you go. Your program has been run, and whatever instructions it contains should now be executing or already be done. Again, instructions, object data itself, logic, all of it is ultimately converted into bits, zeros and ones. The computer speaks in bits, and so this must be the case, no matter what programming language you're using, no matter what use case you're applying it to. Okay, so final topic. I hope you're all hanging in there. We're almost through the content for this class, so just take a deep breath. So now that we've understood the general concepts of code and how it can be written and how it is compiled and run, I want to get into some of the basic concepts of coding itself. If you were a programmer and had to sit down and write a program, what are the things you'd want to consider? One fundamental lesson in coding is that clean and efficient code should always be the goal. You can write the same program in many ways depending on the complexity, but to be able to write it in the cleanest, most efficient way is what is often referred to as elegant coding. I'm not kidding you when I say this, but coding at its highest levels really is an art form, and there's always the brute force way of doing things and then the elegant way of doing things. So let's touch on some of the concepts that are part of elegant code. We're going to use the syntax of the Java language, just because that's the one I'm the most familiar with. Here's an example for us to work with. So here's a really stupid example highlighting something called functions, which organize repetitive code into a shared block. So on the right-hand side, you can see the brute force way of doing things. Here I define two variables, which are numbers. So they are ints, a and b. A contains 1, b is equal to a, so b also contains 1. Then I calculate the perimeter of this rectangle, and that is equal to 2 times a plus 2 times b. So perimeter now contains the number 4. And area, which is a times b, contains the number 1. So perimeter 1 is 4, area 1 is 1. And then for whatever reason, I want to multiply perimeter by area and then print out that product. So I multiply 4 times 1 and I print it out. So I print out the number 4 in line 8 on the right. Then I define two more variables, c and d, both of which now have the value 2. I calculate the perimeter and I store it in a variable, perimeter 2. So 2 times 2 is 4 plus 2 times 2 is 4, that's 8. So perimeter 2 contains 8, and area 2 contains 2 times 2, which is 4. So now perimeter 2 is 8, area 2 is 4, and then number I care about for some reason one more time is I multiply the perimeter by the area, 8 times 4, that's 32. I print out the number of 32. Finally, we do the same thing except for the number 3. So now E has 3, F has 3, the perimeter of that is 12, and the area of that is 9. And then I print out 9 times 12, which is 108. And so now I've printed out the number 4, I've printed out the number 32, and I've printed out the number 108. That's 24 lines of code to print out 3 numbers. And I've done the same exact things in each. There's 3 real blocks here, right? Lines 1 through 8, lines 10 through 16, lines 18 through 24. In each of those blocks, the only thing I've really changed is the number. So in the first block, the number was 1, in the second block, the number was 2, and the third block, the number was 3. And so instead of doing all that in 24 lines and just copying and pasting those lines of code, I can do what I do on the left, which is create something called a function. The function is going to take in as inputs 2 numbers. It's going to take those numbers and calculate the perimeter. It's going to calculate the area, and then it's going to multiply the perimeter by the area and return it. And then these 3 lines are basically going to take advantage of this function. So calculate number I care about is the name of the function, and I'm going to pass in the numbers 1 and 1. This will then return to me 4, which I will then print. This line is print the same thing, but for 2. This line is the same thing, but for 3. So the main takeaway is that both these blocks of code do the exact same thing. And you can see here we've dramatically reduced the number of lines of code and the number of variables we need to define by capturing the repeated logic in something called a function. So functions are also neat because they're nice ways of organizing logical blocks of code into blocks that can be called at various points in your program or by various programs that have the same logical needs, creating more legible and reusable and thus clean code. In the above example, we made things more clean and organized, but not necessarily too much more efficient. At the end of the day, despite putting repeated blocks of code into functions, we still had to execute the same amount of total commands to achieve the result we wanted, right? So 24 lines of code became 8 lines of code, but the 8 lines were executed, a couple more times. So all in all, we executed the same total number of lines of code. One just looked better than the other. The function was called multiple times. So in terms of performance, the cleanliness did not reduce the amount of time it took to complete the program. So to highlight how some code can be more efficient than other code, we have to look at something called runtime. Runtime describes how algorithm performance changes as input size in that algorithm changes. So say you have a list of unsorted numbers that you want to sort. 5, 3, 10, 2, 4, 9, and 1. There's a lot of different ways, that is, there are many different algorithms that you can use to sort this list, and each of these different algorithms can have a different runtime. The notation that is used to describe the runtime of an algorithm or a process is called Big O notation. And while it might seem complicated, it's not that complicated. Basically, all it's measuring is how does your execution time, that is the time taken to complete an operation, let's say to sort a list of items, change when the size of your input changes, so as your list gets bigger and bigger. So let's say you have 10 unsorted items in a list, and sorting that list takes 10 seconds. Let's say that list size changes to 100 items, or 1,000 items, or 1,000,000 items. How does the execution time change? So to highlight this, let's go over some very simplistic examples that demonstrate that point. So again, you have a list of 10 items that takes 10 seconds to sort with a given algorithm, and then you run the same algorithm on a set of 100 items or 1,000 items, and the execution time stays approximately 10 seconds, regardless of how many items are in the list. That's called O of 1, or constant time runtime. That means your algorithm is pretty freaking awesome because it runs in the exact same amount of time regardless of how big your input list is. In the same example, if 10 items takes 10 seconds to sort and 100 items takes 100 seconds to sort, that's O of n, or linear growth runtime. The execution changes consistently in a linear fashion with the size of the input. 10 items, 10 seconds, 100 items, 100 seconds, 1,000 items, 1,000 seconds, 1,000,000 items, 1,000,000 seconds to sort. In the same example, if 10 items takes 10 seconds to sort, and 100 items takes 20 seconds to sort, and 1,000 items takes 30 seconds to sort, then that's O of log n, or logarithmic growth runtime. This is getting a bit too mathematical maybe, but basically this means that the runtime isn't unchanging, like in O of 1, but it's also not linear. It's somewhere in the middle. So instead of 100 items taking 100 seconds, 100 item takes 20, and 1,000, instead of taking 1,000, 1,000 takes 30 seconds. So it is growing, but it's not growing linearly. So let's say to sort 10 items, it takes 10 seconds, but then to sort 100 items, it takes 10,000 seconds. That would be O of n squared runtime. That's quadratic growth, and that's not good. At the end of the day, you want to use the algorithms that have better runtime than the other options that are out there. That is, that are lower on this scale that you see on the right-hand side of this image. So O of 1, if your algorithm runs in the exact same amount of time, regardless of the input size, you're golden. But if it scales in a quadratic way or in a linear way, you might want to look at doing something a bit differently to get it to either logarithmic or something a bit better. And again, the most commonly used example to highlight this is the different algorithms used to sort a list of unsorted numbers from lowest to highest. So again, say you have a list of unsorted numbers, 5, 3, 10, 2, 4, 9, 1. There are different algorithms for performing the same operation. Some algorithms have a better runtime than others. So the way that I would think about this is like, let's say you want to make a carrot cake. There's 20 million recipes probably out there for making a carrot cake, or maybe they're not, like 10 or 20 or something like that. But there's also 10 or 20 different ways of sorting an unsorted list. And each of those has different performance. So improving the runtime improves the performance of your algorithm. And so again, the table on the right here shows a list of different sorting algorithms and their various runtimes. You can see that selection sort is the worst, right? You can see the O of n squared in the best case, the average case, and the worst case. So that's not good. You can see that insertion sort and bubble sort are improvements. So you can see insertion sort has actually in the best case an O of n runtime, and best case means that, well, the list is already sorted when you get it. So the algorithm, it just looks at it and says, it's already sorted. I don't need to do too much work here. In selection sort, even if you get a sorted list, it still takes a lot. It still runs an O of n squared capacity. And then finally, merge sort and quick sort are even better because they give you O of n log n in the average case, which is better than O of n squared in the average case. And then you can go even further than that, and you can see that radix sort and bucket sort have more of a linear average case. So as you work from the top down here, your average runtime is getting better from O of n squared to O of n with the radix sort. So again, I want us to stay away from diving too much deeper into code, but the main takeaway here is that there are different algorithms for performing the same operation based on the runtime of the algorithm. Some algorithms are better than others. You want to use algorithms that have better runtime. And zooming out again, the thing to always keep in mind is that the goal should always be clean, which means succinct, readable, and clear, and efficient from a runtime and a memory usage perspective code. Whenever interviewing candidates, maybe you're looking for your next engineering hire or evaluating existing code bases or products. Maybe you're looking to buy another software company somewhere down the road, or thinking of like their like valuation. You want to make sure you're looking at their code base, and you want to be evaluating on these factors. It's pretty easy to tell when a code base is well managed and when it's not. And things like clean and efficient code are pretty good metrics to keep in mind on that front. On a related note, these two books are really solid on writing clean code and are considered must-reads within the development community. They're very boring, but if you're into it, you're into it. I read the one on the left and made it like a quarter way through on the one on the right earlier in my career. Not gonna lie, they're difficult to get through, but they do help if you're looking to get into software development yourself. And so that's it for class 1. To recap, we first learned about transistors, binary, bits and bytes, and logic gates, all of which are the foundational concepts of all code and all programming languages that exist in the entire universe. We then defined algorithms, programs, and programming languages, and learned about the various types of programming languages and reviewed some of the more common ones in the current software landscape and what they're used for. We then moved on to cover how code that is written in a given programming language is ultimately converted to zeros and ones when the program is run. And finally, we covered some important aspects of code, defining a few ways in which clean and efficient code can be written. Next class, we'll be zooming out and diving into the stack with a focus on the front end. Everything from how does the internet work to IDEO's design thinking framework. Until then, everyone, and thanks for listening.